Now, differentiating log functions gives us a somewhat surprising result, although the working that we need to follow is actually quite straightforward. Let's start over here in this red box with something we already know. If y equals e to the power of x, then when we differentiate y with respect to x, in other words, find dy dx, we just get itself. It's just e to the power of x. We already know this. So to work with a log function, the first thing I'm going to do is just rewrite it. We know that we can retell the story here and say e to the power of y equals x. So that's what I've done here. I've written x is equal to e to the power of y. Now, instead of differentiating y with respect to x, I'm now going to differentiate x with respect to y, and that's what I've got here. So if I differentiate x with respect to y, I literally just get itself. I'll get e to the power of y. And that happens for the same reason as it happens over here. And we've already discussed that. Now, what does this mean? Well, it also means that dx dy could be written as not just e to the power of y, but something that's equal to that. Oh look, x. X is the same as e to the power of y. So I can actually write that dx dy equals x. Now, how does this help me? Well, I want dy dx of my original function, not dx dy. So I'm basically going to take the reciprocal here, flip my dx dy upside down to make dy dx, but I need to flip x upside down as well, and that will give me 1 over x. And that's our basic rule now. When we differentiate y equals the log of x with a base of e, we get 1 over x. Now let's practice using this. Of course, when we're differentiating something that has 2 terms, we just differentiate them one at a time. So the solution down here, if y equals x plus the log of x, whoops, I don't want an equal sign, I want to write dy dx equals, well, if I differentiate the first term, I get 1, and if I differentiate the second term, I get 1 over x. It's as simple as that. For the second one, again, I've got to differentiate one term at a time. So for the first term, I can differentiate 5x squared to get 10x, and for the second term, now here I've got a constant in front. This is fine, the constant just stays there like usual. So I've got minus 7 lots of 1 over x, and that's easiest to write just as minus 7 over x. See what we've done there? We've got minus 7 lots of 1 over x. So you can probably be able to jump straight to that line and put the answer down. If you prefer to do this working, go ahead and put that in, and then jump to this line for the next line down. Now, something that's worth noting algebraically is that for a basic log function, and we know the shape of this, it has an asymptote here, it goes through 1, and it comes up like this. We can see that the first derivative is 1 over x. The second derivative, if I just change the form of the first derivative like this, you can clearly see that differentiating again gives me this, but it's a little bit neater when it's written this way. Now, any number that's squared is positive, so 1 over that positive number will be a fraction, albeit getting smaller and smaller. So this negative out the front means that the second derivative is always negative. And that means that it's concave down for all real x. And that makes sense. We can see that the curve is concave down, but now we have the means to actually prove it algebraically.